Okay, so I'd like to thank the organizers for giving me this opportunity to speak here. So this always feel like a rock concert. Anyway, so I'll be talking about entropy production and linear response in active Brownian particles. So I'll introduce what systems I have in mind, but before that, a little bit of recap of thermodynamics, whatever I'll be going through. So first things are, okay, so we know the first law, second law of thermodynamics, so energy conservation, and then in macroscopic second law, we know that entropy production of the system plus reservoir, and if we write it down in that fashion, so in the reservoir entropy production is supposed to be the heat. So in my notation, it's the system, whatever is absorbs the heat, increases its energy. So heat released by the reservoir to the system, or so that's the entropy production in the reservoir. So that's what, and the second part is we normally look at linear response to look at and look at the relation between the linear response and the fluctuations in the system. That's in equilibrium, but now I'd ask this question that can I develop a stochastic thermodynamic description? Of course we can, for active Brownian particles. So taking the stochastic regimes of thermodynamic quantities and also looking at response functions. Okay, so before I get into my system, so to set up the language, so we'll be looking at Brownian motion. So Brownian motion means that I have a larger particle sitting in a bath of smaller particles, and then there is a length and time scale separation between the large particle motion and the small particles. And so then if you look at this, the larger particle will undergo random movement in this bath, and then one can write down the equations in terms of the position and the velocity, where this part is the energy, this part is the forces coming from the heat bath. So this is the dissipative part, and that's the fluctuation, and I obey the fluctuation dissipation relation. So if I switch off all my activities, my system should go back to my equilibrium system. So, and then starting from this equation, one can just multiply with the velocity, write down an equation for energy conservation. So it just has kinetic energy, which will be now given by the heat absorbed by the system, by this system, means this single bead floating in the heat bath. Okay. So, yeah, so the simplest way we can drive the system out of equilibrium is to put some external force on the system. So then one will give a directed force and write down the Langevin equation in presence of this directed force, and that changes the stochastic energetics to energy conservation will be now given by the total heat absorbed by the system and work done on the system. So that's the rate of work done. So I'm just using standard well-established notions, and much of these notions are established by Udo, and so he has several review articles. I particularly like this Fizdev letter one-page argument in that. So entropy. So there are two ways one can now, if I go out of the energy conservation picture and then look at the entropy production. So if I drive the system out of equilibrium, if the time reversal symmetry is broken, the system should be producing entropy. And then we can calculate entropy either from first writing down equation for the probability distribution, a Fokker-Planck equation, or you can also look at the probability of forward and reverse trajectories, and then taking a ratio of these trajectories and defining entropy from there. So I'll just give you a brief outline of the this description before I get into my system. So we write down the Fokker-Planck equation. I am writing it down in dividing the total current into reversible, so should be dissipative, JD, reversible and dissipative part of the current. And then this divergence, this gradient operator stands for the positional and velocity differentials. And The reversible current part is given by, first is the velocity of the particle, second is this external force, which I assume that under time reversal, this doesn't change its sign. And the dissipative part of the current, so for positional side, it has nothing. For the velocity component, it has two parts. One is coming from the dissipation gamma, and then the other part is from the stochastic forces. And then one can write down the total entropy in the system in terms of integration over dx and dv, the phase space integral, and write down a time derivative of this entropy production. So entropy time derivative, which is the entropy production, then can write this down in terms of del del t of p, plug in this relation, couple of steps of algebra, we can write it down as, so first is log p and divergence of these currents, and then performing a couple of steps of algebra, you can separate it out. So one part is that log p divergence of current, we can write that down as a divergence of reversible current divided by the probability and average over that. So means that this is p d gamma integration of this. So this quantity occurs within the system, this goes to 0. Trivially this goes to 0 because there is a derivative with respect to x on v, so that will give me 0, and this component itself is 0. So that's trivially 0 here. And the dissipative current, if I look at that part, one can write that down in terms of one part which is always positive. Dissipative current, I am looking at this velocity component, means this part minus gamma vp minus d0 del vp, that part here. So that's always positive, and there is this extra bit. And if I take this extra bit to the left hand side in s dot plus this extra bit, that the whole thing is greater than equal to 0. And this extra bit, we can then show that this extra bit is like a heat, so like the entropy production in the reservoir. So that's q dot by t. So I have this kb sitting here. So q, what we are getting is that this is a q dot average over trajectory and distribution, as nicely shown in this article. So you can write this down, the reservoir heat production, as an average over this q dot, where the q dot itself is the heat production as we have seen from this relation. So V times minus gamma V plus eta, so that's the work done by the reservoir, that's the heat production. And that's in sync with the Clausius expression of the entropy production in the bath. So you can do that from the time forward and time reverse path probabilities as well. So what we do is that I just describe this, give the outline. So if I take any trajectory, so under external drive, still the system is under external drive, I start with the probability distribution at time equal to 0 and evolve the system up to time equal to tau, and the system evolves, and I can look at the path probability distribution of the system as it moves forward. So that thing, then the whole path I can chop it up into small segments over some time steps delta t, simplifying this whole path integral. And let's say that's on an ith segment, this probability is pi plus, and then after this propagates, after time forward propagation, let's assume that the system goes to a final state, and from the final state defined by this final value of the force, could be some f at tau. So what is the probability of system? So I start from another configuration of the system which obeys this probability and then reverse it back. So via this reverse trajectory, so reversal means that positions doesn't pick up sign, velocity is odd function, picks up a sign, force is an external quantity which doesn't pick up a sign. So you put this together, then you can write down the probability of this forward path, which will be apart from a Jacobian, which will be given by the probability of the reservoir noise, eta I, which we assume to be a Gaussian noise, and which obeys then in presence of this constraint that they have to follow the equations of motion. So if one does this calculation and calculates the forward and reverse path probabilities and ratio of that on this ith segment, you can write it down as minus beta, which is 1 by kbt times delta t, the time step over this segment, and heat produced, heat absorbed from the reservoir q dot at that ith moment. And then for the whole trajectories, you can write it down as an integral, so multiplication of this whole thing. So that will be written down as an integral over the whole time evolution tau dt times q dot, where again the q dot is really the heat production, heat absorption, as we have seen from the first law. And then one has to also take into consideration the entropy in the initial state, entropy in the final state, so the stochastic version of this entropy, and then you club them together, the total entropy production will be given by the entropy change in the system, which is given by the difference S tau minus S0, and then the heat entropy production by the reservoir during this transition from the initial state to the final state, which is given by the total heat absorbed from the reservoir. So this should be a minus sign, minus q dot t. So then one can show using this relation, this forward probability and reverse probability ratio, one can show that the total entropy production in the forward path, delta st, that probability of that, and the ratio of the minus delta st, they obey this detailed fluctuation theorem structure. And of course, it's related to the integral fluctuation theorem, which is again related to Jarzynski equality, etc. So these are the things we can get from single Brownian particle driven by external forces. But now I come to the active Brownian motion. So of course I don't have to motivate this active Brownian motion to this audience. We get to see activity in various biological situations, for instance, motor proteins, E. coli motion, cell division, active colloids, and maybe neural growth cone motion. So some simulation of active colloids. So many such things in which the main issue is that individual particles, as the conference website also says, that individual particles are self-driven, self-propelled. So they have some internal energy source. They use that. So the forces drive comes from the smallest scale, not from the largest scale. So that's activity. So then my plan is to give a couple of models of activity, which we will be using some active force model, velocity dependent models. And then I'll give you outlines of fluctuation theorem and some modified fluctuation dissipation relation that's obeyed by these systems and some simulation results. Okay, so before I get into the models, a little bit of motivation why this specific model we are taking. So let's say these are experiment I have taken up from this reference. Let's say there is this fan which has blades which are all symmetric in both sides. All the blades are symmetric in both sides, and then there is this kick from this granular material which is being vibrated vigorously, and they are kicking the whole thing, and this moves either rightward clockwise or anti-clockwise. So this thing being completely symmetric, if you look at the velocity, rotational velocity distribution, you'll see that as you increase the kicking of the whole stuff, of course the measurement depends on the time window over which one measures the velocity. So, but over that time window, if you don't change the time window, you can see that the distribution of velocities picks up a sort of symmetric distribution where there is a positive and negative velocity peak. So maybe I can run it once more. You'll see that these guys make these blades move clockwise and anti-clockwise, stochastically of course. And so this is weak driving, this is strong driving, in which it moves for some period it moves in one direction, some other period it moves in the other direction. Okay, so I think this is a movie of the asymmetric vane. So one set of experiments were done where each blade is symmetric in both sides, another set of experiment is done where one side is different from the other side. So this asymmetric thing then rotates in a specific direction, and then you will get a velocity distribution which also picks up a little bit of negative peak, but mainly it remains positive. So what I'm trying to show is that the velocity distribution in this system, the effective system which is rotating, that velocity distribution could be both symmetric, could be asymmetric, that depends on the system itself. If you make the system symmetric, that it's symmetric. Then there is this two surfaces of the blades. So I don't really remember now exactly how the asymmetry is generated, but this is asymmetric in the way that if it rotates rotating in one direction is favorable than rotating in the other direction, then you are kicking the whole stuff. So the next set of motivation comes from this old experiments and theoretical explanation of the experiment. So this is an experiment about a microtubule which is being driven by kinesin like molecular motors. One kind is this normal NCD motors which will take the microtubule in a specific direction. Each individual motor moves in a specific direction and many of them are carrying this microtubule. So the microtubule is as a whole carried in a specific direction, and if you look at the velocity distribution of that guy, so sort of how many times it's going forward and how many times it's going backward. So if you look at that guy will show a positive motion, positive velocity in a specific direction. So that depends on the orientation on the microtubule. On the other hand, there was this other protein which belongs to the same kinesin family, NK11. So this guy behaves like a symmetric ratchet, in which essentially the microtubule undergoes a symmetric motion. So it shows you some period it shows a positive velocity, other period it shows a negative velocity. So you have to imagine that single microtubule being driven by many of these motors together. And then the symmetric case, obviously this distribution looks like a symmetric distribution which can be captured by velocity dependent potential, and the velocity dependent potential then can be used to write down a velocity dependent force which was being written for that specific case, and certain experimental results could be analyzed using these equations. So, but if I write down this equation of motion in presence of such a velocity dependent force, this is called the Rayleigh-Helmholtz model. And this model, so main thing we should focus on is that this velocity is, the force itself is odd in the velocity variable. So if I take velocity t going to minus t, velocity will pick up a negative sign and these forces will pick up a negative sign. So this is unlike the external force, it picks up a sign under time reversal. So then there is another class of models, it's called energy depot model. So this, like, to describe a naive description of motion of a self-propelled particle. So what you can do is that we can say that the particle is moving because of an internal energy depot, and the energy depot has a dynamics of itself, and part of the energy is supplied to the motion of the system. So what could be the naive dynamics of such internal energy depot? That, let's say I'm thinking about a bacteria. The bacteria eats some food, so that's the energy increase, the gain term. Then it has to metabolize, so a part of the energy will be lost to metabolism. And then there will be a part of the energy which will be utilized for motion of the bacteria. So if I use that part of energy, so simplest would be if the bacteria doesn't have forward, backward symmetry breaking, if going forward, going backward is equivalent for the bacteria, then we can imagine that the energy lost to motion should be, to smallest order, should go as v square. So should be symmetric under V positive and V negative. So it doesn't matter whether the bacteria moves towards right or towards left. It has to use up energy. So that part of energy, if I then write it down, so this is like a energy dissipation, which is like a force times a velocity. And this force will go to the motion making of the bacteria. And that force, then I can use this relation. That force will be then given by the instantaneous energy of the bacteria, Et, times this velocity. But we can use a simplification, say that the bacterial internal energy depot equilibrates faster. So the dynamics is much faster, not equilibrate, it goes to a steady state faster. And if it goes to a steady state, one can use a steady state assumption. And then you will get a steady state energy which is even in velocity. And as a whole, you will get a force which is again odd in velocity. So with this motivation now, in the first part, let me show that what will happen if I just use velocity dependent forces where the force is odd under velocity, so under time reversal as well. So first thing is simple. So if I try to look at energy conservation, I'll get an energy conservation. So this part and the potential energy together will make the total energy. And then there is a work done. Work done is just force times, external force times displacement for the bacteria. And then I am left with two pieces. One piece is my original energy from the reservoir. So that's the heat. And there is an extra piece, which is some kind of a force times velocity, where the force is coming from the internal energy depot. So we can also, at this stage, interpret this as another reservoir which is internal to it, and that reservoir is supplying this amount of energy. So then we would expect that from here, if everything was fine, I should have got a total entropy production in the reservoir, which is just addition of these two terms. So what we see is that the unexpected part is that this doesn't hold. So we have some extra bit on it. So we just use our normal, so we can either use Fokker-Planck equation or the time forward, time reverse trajectories to calculate the entropy production. So same algorithm if you use, so of course there will be a Jacobian sitting here, but in this specific case the Jacobian drops out under time forward and time reverse probabilities. So if I take that ratio, so in the ratio what comes out is that apart from the total heat absorbed by the system from the reservoir and from the internal energy in the mechanical degrees of freedom, apart from that there are these two extra bits. And these two extra bits, so first bit you can look at, so this is given by a cross, this is a cross term between the force production due to the internal energy bath and all mechanical forces, external force or potential, etc. This is a cross term between the two. And the last part, this delta phi, is coming from the velocity generation by the activity of the bacteria. So this is just minus del phi del v. So with respect to velocity, it acts like a potential. So and then you can do the regular stuff and show that the entropy production in the reservoir has this extra part, extra bit, and of course this whole thing obeys fluctuation theorem, but this extra bit is really coming from the crosstalk between the internal energy bath and the mechanical degrees of freedom. Everything else follows the integral fluctuation theorem, detailed fluctuation theorem. At steady state, we are now thinking about a specific steady state under constant drive. And then you have this total entropy production, which has this extra bit. So this extra bit is the thing which is the main, I'll say, new result, and we don't understand exactly. So understand in the sense that if I try to interpret it in terms of really two baths, so I would have liked to see something where there are really heat dissipation in the baths to begin with. So maybe I start with something like an equilibrium bath, and then if I come to a non-equilibrium counterpart of it, then we should see where from these extra terms are coming. So we can see within this calculation where from they are coming, but that's just within the specific models. So models which are given by this velocity-dependent forces which are time reversal asymmetric. So of course, if you switch off these velocity-dependent forces, as I assured that we'll get back this delta qm. So if the moment I switch off velocity-dependent forces, all these extra terms drop out because everything has this bit of fv. So they drop out and we get back our original Clausius form of reservoir entropy production. And then of course it obeys Jarzynski equality, etc. So then if I come to our system and ask this question that what is the minimal condition under which the system shows breaking of detailed balance? So I wrote down the full Fokker-Planck equation of the system. My reversible and irreversible parts of current I list down here. And the detailed balance condition will require that irreversible current is 0, while the divergence of reversible current is 0. So you have these two equations. Now if I put these two equations together, I get this relation. So this relation is something where I have in the left hand side everything is a function of velocity. On the right hand side, this guy is only a function of velocity, but this guy is sitting here with a function of position as well. So this cannot be true unless I set ux equal to 0. That's one possibility. Or if I set this fv is proportional to velocity itself. So that's like putting this time only using only minus gamma v as the velocity term. So that's like equilibrium bath. If I just use equilibrium bath, I am at equilibrium. Else I have to set ux equal to 0, then the system will behave like in equilibrium. So detailed balance will be obeyed, and one can also write down the probability distribution which will have a different structure but obeys detailed balance. So it shows us a possibility that even if I take this particle and put it in a harmonic potential, it will start to produce entropy. So I don't have to really use external drive to produce entropy and drive the system out of equilibrium. So the system will go to non-equilibrium, but by itself, free system is still obeying detailed balance in this case. So first thing, simpler thing, if I put just an external force, the system produces entropy. So this is the probability distribution of the velocity, and the entropy production, these are the distribution of entropy production. So this is, I just wrote down the expression of the entropy which we used to do this calculation numerically. And if I take those probabilities, they obey the detailed fluctuation theorem nicely. The second thing is, if I put this particle under external trap, just a harmonic trap, it's again driven out of equilibrium and it produces entropy by itself. So it starts to behave like a self-propelled particle. And then these are the entropy production, the probability distribution of entropy production, and again it obeys the fluctuation theorem symmetry. So for this system, then the next question I come to this fluctuation dissipation relation. So the response function one can calculate by using the noise in the system, treating it as equivalent to the external forces, and then we get this relation where noise is involved, and then we can use our equation of motion, and using those, so some steps of algebra, one can show that the velocity response of this system in presence of this external harmonic trap, that has this structure where I have a correlation of this G. G is taking care of all the time reversal asymmetric part, velocity dependent parts like minus gamma v and the external force F of v. These two together I am calling that G. So this guy, of course, if you are driving it out of equilibrium, this correlation is not equal to that correlation, and that one can also show explicitly, and one can separately calculate it. So what the next thing I'll show is that we can separately calculate this correlation and that correlation at a steady state for active Brownian particle in a harmonic trap separately, and then we drive it and look at the response and compare these two. And of course, if I just put GV equal to minus gamma V, I trivially get back the equilibrium fluctuation dissipation theorem. So this is the response. So what I'm showing in the first graph is the response function for within this harmonic trap for the passive particle and for the active Brownian particle. So active Brownian particle shows much longer correlation and longer time of oscillation. And then here I'm showing the comparison between the fluctuations, steady state fluctuations, with the response under small external kick. So they match well. So then I come to our next generalization of the model. So this part, earlier I said the external velocity dependent force, what I am introducing is asymmetric under, so is odd function of velocity. So now if I use both bit, one is an odd bit and an even bit, so I assume that the velocity dependent external force can have both an odd function of velocity and an even function of velocity, and if I can separate them out. So one is even and another is odd. And then I go through the same steps. You will see that the reversible part, now reversible part of the current, will have this odd function of velocity sitting here. Sorry, the even function of velocity sitting here. And the odd part, like the minus gamma phi, goes in the dissipative part of the current. Strangely, as you will see that if I now use this entropy production, so we have again used the Fokker-Planck route and the time forward, time reverse path route to calculate the entropy production in the reservoir. So I'm just showing the Fokker-Planck route. Both these results match with each other. I'm showing the Fokker-Planck route, and so first part, the reversible part, as I showed earlier, so we'll have a P times divergence of JR by P part, which now for this specific case is not zero. So this is a velocity derivative of this even function of velocity, the active force, which is even function of velocity. And then in the total entropy production, I have this part and extra part, which is the dissipative part of the current. So I just look at the total dissipative part of the current and pick out this bit. So this bit of the dissipative part of the current, the other bit is 0. So I just pick up this, and that I am calling the scalar dissipative part of the current, and that scalar current and the G of V, which contains all the odd velocity dependent terms, minus gamma V and the odd part of the velocity dependent forces, that together. So if I take them, so that together ultimately generates the total entropy production in the reservoir. So in the total entropy production in the reservoir, apart from the heat, dissipated heat absorbed from the environment, then there is energy produced by the internal energy depot that comes to the energy flux. So that two of them are in this Q dot. And apart from that, we have this all extra terms. And in this expression, remember that I am not using the external force anymore in this expression. So even if I don't have external force, I'll still have all this, because I have the odd part of the velocity and the even part of the velocity, they are coupling together. And these guys together are all of them together constitute the non-Clausius dissipations in reservoir. The reservoirs I cannot point out now. So because these are all coupled between, so these are coupling between the odd, this guy's psi is given by the, so this is a velocity dependent potential which will give rise to the odd part of the velocity dependent force. Then this QEM dot contains a odd part coupling with the even part. Even if I don't have external force or external potential, these extra bits will come in. So, but rest of the things follow, like the total entropy production. If I use this entropy production in the reservoir, that obeys this fluctuation relation symmetry, and the total entropy production has this strange structure. Then what I can do is that I can do a simple thing that I can simulate this. So I take a particle in which I use this external velocity dependent. So I'm saying that this particle is driven by the velocity dependent forces, and this velocity dependent forces has, in general, can have both odd and even parts. So one part is like the odd part, which is the velocity dependent potential will generate these even functions. So these are this v squared and v4 terms, and another could be a v cube term, which will give rise to a force which is v square order, even part of the force. So if I take them together, I can write down the probability distribution, and that matches well with the simulation results for the probability distribution of the velocity. And then I use this simulation to calculate the entropy production in the system. The entropy production has this strange kinky kind of shape, but what still it obeys the fluctuation, detailed fluctuation theorem, this symmetry quite well. And of course, we don't, for this system, we don't require any external potential trap or external forces to drive the system out of equilibrium. The moment I have both odd and even function of velocity as the velocity dependent forces generated from internal path, they will drive the system out of equilibrium. So then the last thing what we are doing right now is that if we write down a full stochastic version of the energy depot model, so keeping a heat bath term, so a particle moving in presence of this heat bath, and where this guy is coming due to the coupling with the internal energy depot, and the internal energy depot obeys this original gain term, these two loss terms, and a stochastic energy term in this. And then you can follow the Fokker-Planck route or the time forward, time reverse path route and try to calculate the entropy production in the reservoir. So again, the total entropy production we can identify. So this is even more horrible. So this entropy production, although you cannot see much, so this new, now I am writing it down as something which can be both odd or even function of velocity. So some terms are odd, I'm writing them new odd, and some terms are even. And then, of course, I've not separated out the heat production in the reservoir here, but you can see that this bit has V dot minus this term, and V dot minus this term will contain the heat production, the reservoir force generation, and that can multiply with this minus gamma V to generate the original heat production term, but there are many more extra terms coming just due to the internal activity. So I hope I could convince you that at least within this set of active Brownian particle models, where the activity is coming due to the velocity dependent forces generated from the internal energy depot, that gives rise to several non-Clausius entropy production term apart from the normal heat bath entropy production. So, and also we can write down the response function in terms of some modified fluctuation dissipation relation. So with that, I'll stop and thank you for your attention.
I mean, perhaps a little more comment than a question. I mean, obviously, it's kind of difficult to interpret the terms which you get from this formalism as entropy production. And I will show tomorrow another case which shows that this quote-unquote naive idea by looking at forward and backward trajectories does not really lead to what one would call perhaps physical entropy production in terms of heat. So my suggestion would be to come up with a more microscopic model which mimics or reproduces this kind of f of v behavior. And then the whole issue of entropy production would be clear, because for the microscopic models, it's pretty clear what physical entropy production is.
Right. So here, so I had been thinking in this line. One problem is with the energy depot kind of models is that the other equation is the equation on energy. That's not in the same status. So, instead of that, to probably one possible way could be, so I was thinking about it, didn't try it out. So one possibility could be that if one takes two beads connected with, let's say, a spring, and say that the first bead is coupled to the, so it's a bigger bead which is looking at the external world, and there is something internal, so which can be mimicked by the second bead, and it could be a different reservoir, for instance, could be a correlated noise reservoir. Correlation often people use for modeling activity, and then one can try to separate out. So my in one thing I'm getting convinced about the calculation. So I'll also ask you this question that entropy production, we can write down the entropy production structure of the entropy production from time forward, time reverse trajectories. That's one. Another possibility is that we can take the Fokker-Planck equation of the whole system and then try to identify what are the entropy productions.
Yeah, but in both cases, if for these kind of phenomenological models, it will be more a kind of effective entropy production on some higher level, and you will typically not get the heat, for instance, which would come from a real physical process. So in any case, I mean, you know, we're used to play these games now for 10 or 15 years, but if we do it for these coarse-grained models, we should accept the fact that we get something, but it's not necessarily what you would call physical entropy production.
Right.
Any other questions? Yeah.
So when you look at the response here, like it's sum of two parts, right? I mean, and so I mean, can you say like how it compares with this formalism of Christian Mays et al., where they also have this response in?
So this sum of two parts here are the correlation of the one part is nonlinear in velocity. One function is nonlinear in velocity. So this nonlinear velocity function times the normal velocity term. So this is a nonlinear part g of v at time t and v at time 0. And then the other part is actually just reverse of that. V at time t with g of v at time 0. So these two terms, then once you make them both linear, then they are equivalent to each other. Then they add up and gives rise to the normal fluctuation dissipation relation, what we know. But this guy is, because it's a nonlinear term, and the system is driven out of equilibrium, time forward and time reverse are not same. So g of v at t and v at 0, that correlation is not same at v at 0 and g of v at t at time correlation.
So my question was, what does it relate in any way to this?
So frankly speaking, I don't understand. I mean, those papers.